Hey guys, for today we have some notes again to go over systems of equations, which is going to kind of combine something we've already looked at, which is standard form of linear equations, moving them into slope-intercept form so we can graph them, but we're going to graph two linear equations on the same coordinate plane, and that is what systems of equations looks at. It's the collection of two different types of equations on the same plane to see if there's a solution or some sort of ordered pair that would work for both. So this is going to be page 61 in your notes for today, coming behind yesterday's notes. So I'm going to flip to that now. And here we are. So for this page that is attached to your Google assignment, it is actually glued into the notebook sideways. So my notebook is longer than it is wide, so we glued this in sideways. This is another one that's going to go kind of the opposite way of our actual page. And this is the page. So we're going to start at the top, and again, most of it is already here for us. We're just filling in the blanks. Down here, we're going to have to work some stuff out to get our final equations, which will be very tight with a small amount of space. So bear with us, and then that is it for your notes today. I don't want this video to take too long, so I'm going to go ahead and jump right in. So a system of equations is a collection of one or more equations graphed on the same coordinate plane. A system of equations can have the following solutions. It can have one solution, which is an ordered pair. And this will make sense once we do an example down below. So there is one point that both of the graphs meet at. It can have zero solutions. The equations do not intersect. So that would be parallel lines. If they're both graphed on the same plane, they're never going to run into each other. They're never going to connect. Or it can have infinite solutions, also known as many solutions, which is the same equation, which literally means every single point that one equation has, the other equation will also have. So if you had a line here and then you graphed another line here, all of these points are going to be on both equations. They're going to have a million solutions. They've got the same ones. So we're taking our linear equations that we previously looked at and learned how to graph and graphing two of them together in the same coordinate plane and looking at, is there a place where they meet? Is there an x value and a y value that they both share that would actually run into both functions? Or is there not? Is there never going to be a way that, one coordinate that sits on one line, it's never going to be on the other line? So that would be no solutions. Or are they the exact same? So we're going to look at some examples down below of how you find that from a graph. Okay, and again, we're going to have to write as small as we can. And I'm going to try and use two colors for each so that we can see what's happening. Color coordination in this example is going to be important. So all of these examples look like they're given to us in standard form, which is AX, BY, and C. They're not written in slope-intercept form, which we need to graph. We need it in slope-intercept form so we can see the slope and the intercept, which is helpful. So we're going to have to rearrange it. So I need this 2x to come over here. So now we have negative 5y equals negative 2x minus 30. So I moved the 2x over. I can't combine it with the 30. They're not like terms. I just moved it over. And then I need this negative 5 to go away. So I'm going to get rid of it on the left side, but that means I have to do the same thing on the right side to all three parts. So the final answer, now that that's gone, is going to be y equals, this is not going to simplify, but those two negatives, sorry, you can't see what my hand is doing. Just give me 1 second to get this camera. I'll scoot it over here for you. I apologize. There. this negative 2 over negative 5 isn't going to reduce, but the two negatives do cancel out. So I'm just going to bring down 2/5 the x, and then negative 30 divided by negative 5 is positive 6. So this is the same equation, but now it's in slope-intercept form, so I can graph that. Just by looking at the equation, I have what I need. So I'm going to do the same thing with this equation. I'm going to move this x value over here. I cannot combine those. They're not like terms. So I have negative 5y equals negative 7x minus 5. I always want the x to come first if we're trying to get it in that format. And I'm going to divide that negative 5 away. And it cancels there, leaving me with y equals positive 7 over 5x plus 1. Right? Because a negative 5 divided by negative 5 gives me a positive number, and it's just 1. So now that I know both of these, I can graph them. And I'm going to use the colors that match. So for the pink equation, I'm going to start at 6, and my slope is up 2 over 5. So from the origin, or the middle here, I'm going to go up 6. 1, 2, 3, 4, 5, 6. Put a point. And then I'm going to go up 2 and over 5. And that's going to be my point. A ruler or a straight edge of some sort is going to be helpful. And then the second one starts at positive 1, and it goes up 7 over 5. Which is right there. And again, use some sort of straight edge. Meaning, these two equations have one solution. They meet in one spot. So there is a number that there's an x value that you could plug into both equations that would give you the exact same y value. And that is this point. This x and this y value at this point, no matter which equation you use, will work. It'll work for both of them. So it's a solution that's on both of those function lines, but there's only one of them. There's only one place where these two lines meet. And so this is an example of one solution. Let's move on to the next box. And again, do the same thing. So we are going to move our x value over here. We're always trying to get y by itself. So I start and I see where my x is, and I move that thing first. And then it's on the other side, and I cannot combine it with that 24. So now we have y equals negative 1/6. I can reduce that, plus 2. Okay, because 24 divided by 12 will reduce down for me. And then for this one, move this x over. So we have 6y equals negative x minus 30. And I need the 6 gone. So our final answer will be y equals negative 1/6 x. Again, there's an imaginary 1 right there. So that helps me separate the two. And then 30 divided by 6 will reduce to 5. So it's going to be negative 5. And again, I'm not going to go over all of this again a million times. We've done a lot of notes on going from standard to slope-intercept form, and a lot of notes on slope-intercept form. So I hope I'm not going too fast, but again, we do have notes on this from the past. Oh, I do apologize about that. The lights in this room are timed. So now we're going to plot both of them and see how many solutions we have. So this green equation that I wrote in green starts at 2, and it has a slope of negative 1/6. So I'm going to go up 2 and put a point, and then I'm going to go down 1 over 6. All right, because that's a negative slope. So it's when it's rise over run, but your number is actually negative, you're going to fall instead of rise. And then same for the pink. I'm going to start at negative 5. 1, 2, 3, 4, 5. I'm going to go down 1 and over 6. And connect those. And that will be the function graphed that matches the equation. So, and I can tell this just from the equation, but I graphed it for you guys. They both have the exact same slope, which means they're both going to move the same way. They're never going to touch each other. These are parallel lines, right? If this line keeps going up and over, how am I ever going to get it to run into the pink line unless I literally change the slope? So this would be 0 solutions, meaning there's no number that's going to work for both of them. There's no answer that I can plug in that's going to work for both equations. They don't have a solution together as a team. Nothing works. They have different answers. And then the last example, again, we've got 2 equations. So start by moving your x value to the other side away from y. So now we have negative 5y equals negative 4x plus 20. And take away that negative 5 so that your y is alone. So that's going to be 4/5 x minus 4. And again, when I bring this down, the negative 4 divided by negative 5 become positive. Now I can't reduce the fraction, but the 2 negatives do cancel. And 20 divided by 5 is 4, but because one's positive and one's negative, the answer is negative. Remember, when you're multiplying or dividing, if the signs don't match, it's negative. If you're multiplying and you're dividing and the signs do match, it's always positive. And then the next example has a bit more to it, so I'm hoping we have enough room for this. I'm going to move that 2x over here. So now I have negative 5/2y equals negative 2x and a positive 10. So now I have to do this fraction in pieces. So to get rid of this divided by 2, I'm going to times it by 2, and then I'm going to times this whole thing by 2, essentially. Both of these are getting times by 2. So that cancels, leaving me with just negative 5y equals 4x plus 20. And then divide away the negative 5. Remember, you can't ever get to numerators if the denominator is still there. It traps it. You got to get the denominator gone. So our final answer, now that those are canceled, is y equals negative 4/5 x minus 4. Again, I know that was very tiny. So we're going to graph these. I'm going to, again, color code it. So I'm going to start at negative 4. 1, 2, 3, 4. And go up 4 over 5. Do the same thing with this one. So I'm going to go down to negative 4. My slope is up 4 over 5. I apologize. Actually, I just realized I did something. This is a negative 2, and I did not see my negative symbol. So 2 times negative 2 is actually negative 4, which would make this positive because 2 negatives is a positive. So this is 4/5 as well. So I'm going to go up 4 over 5, which means that this green line is also right here. They're the same. So in this example, there are infinite solutions, meaning no matter what x value you plug in to either equation, it's going to work. If I want to plug in 2 for this x value and I get a specific y value, it'll be the exact same for this one. They will get the same answers because they are the same. There's a million solutions that could work between any of them. So that is the 3 types of examples, and then you have a word problem to do for a day. So I won't do this completely, but I'll get you started, of course. So it says Billy bought 1 widget and 1 gadget for $4. Sam bought 1 widget and 3 gadgets for $6. So we're going to write a system of equations for the situation. So let's make x's be our widgets and y's be our, gadgets. So Billy, we're going to make his equation. Billy bought 1 widget, 1 x, and he bought 1 gadget, 1 y, and it was $4. So Billy would have 1 x and 1y is $4. And you don't have to put a 1 when you're doing these things. If it was just x and y, we would know there's an imaginary one there, but I'm just doing that to help you guys. And then it says Sam bought 1 widget and 3 gadgets for $6. Right? So x's are widgets and gadgets are y's. Now we need to solve this algebraically. So what we're going to do is solve one of them for y, just like we did over here, and then plug that y into the other equation as y. And this is called substitution, which we're going to get into next week some, but I want to go ahead and show you how this works. It's really neat how you can do this. So if we have 1x plus 1y equals 6, and I say solve for y, let's get y by itself. Move this over here. So we now have y equals negative x plus 6, and I just took those ones away because we don't ever need them. So now in Billy's equation, 1x plus 3y equals 6. Instead of writing the y, if I know that y is this, I can replace the y that's in his equation with this. See how his equation has a y here? But we know that y equals this, which means these are the same things. It's like composing a function of a function, essentially. So I'm going to put when we use Billy's equation, what we figured out y is. If y is negative x plus 6, we can put it in place of y. We now know what y is. So I'm going to put it right here. So this equation is 1x plus 3y equals 6, but I'm using this one. And then we're going to solve. So we have x plus negative 3x plus 18 equals 6. I'm sorry. Actually, this is supposed to be 4. Look at that. I made a typo. So that would make this 12 equals 6. Where did I get 16? Oh, goodness. And then we can combine these because they're like terms. So that actually gives us negative 2x plus 12 equals 6. And then move this 12. So we have negative 2x equals negative 6. And divide the negative 2 away. So our goal is to figure out, since we plugged in the y, only letters that we had here were x's. So I was solving for my x. So now x equals 3. So if we look down here at the bottom, the cost of a widget, which was our x values, we just figured it out. One widget is $3. So how do we figure out what the gadget is? Well, if I know that a widget cost me X dollars, we just solved for it. Go back and plug it in. So I'm going to go all the way back up to this equation where we are solving for y. It says y equals negative x plus 4. So I'm going to plug in my x value. I'm running off the paper here. So we have y equals negative x plus 4. So I plugged in the x that we just found, which is 3. What is negative 3 plus 4? It's 1. So I used the x, and I now found the y. The y is 1. So the cost of a widget is $1. And this is called substitution, where you've got two equations like we just saw when we graphed them, and you solve one for y, and then substitute that in for y in the other one. So then you can solve for a missing variable, and then you can use that variable and go back to either one of these originals. Now that you know one of the letters, you can solve for the other. And so this is a really cool way as well. So you can graph them and find solutions, and you can solve them algebraically and find solutions as well, which we're going to get into more next week as well. So that is it for your notes today. Make sure that you get those copied down. That's page 61. And I hope you guys have a good weekend.